Okay, today I want to share with you an invention of mine. It's called a thermal power generator. The basic premise for this invention is based on the thermal properties of liquid ammonia. Liquid ammonia will exert 100 psi per degree temperature that it's raised, Fahrenheit degrees. So if you raise the temperature of a liquid ammonia that's trapped inside of a tube, let's say, or pipe, and you raise the temperature of that ammonia 100 degrees, you will have 10,000 psi pressure. So based on that principle, and applying it to a boiler, waste heat of a boiler, because you have boilers in hotels and in hospitals and commercial use throughout the United States. So there's plenty of resources, and boilers are known to have what is termed as waste heat. Goes up the stack. It's the heat that's left over from use of heating water to making steam or hot water. And basically the basic stack is about 20 inches in diameter. It has about 350 to 500 degrees that is normally going up that stack, and it goes at a rate of about 10,000 cubic feet per minute. So you got a resource there, and what you would do is hook the heat exchanger, your ammonia heat exchanger, through a bunch of ducting systems up to the boiler stack with a fan that will draw off the heat off that boiler with an airflow of 3,000 cubic feet per minute. So you have a modulator here that will either draw from the stack or it will draw from your ambient air. Okay, so it's cyclical. It works on a cycle. You raise the temperature, you'll raise the pressure, you'll lower the temperature, you'll lower the pressure. So your up cycle, you'll be drawing off the boiler. It will run hot air across these ammonia tubes and back out into the atmosphere. You will usually go from around 50 degrees to start with on an average day, or 70 degrees. And then it will raise it 100 degrees. So if it started at 50, it will raise it to 150. It will then it will expand in here, and it'll exert pressures up to 6,000 psi. At that point, any pressure that it continues to try to exert will actually be used to push this hydraulic fluid that goes down to an actuator. This is a hydraulic actuator. As this expands, it causes this pressure to build up to about 25,000 pounds force on this piston, which will drive this rack, and drive this actuator, which is connected to a rack and pinion system. That rack will drive that pinion. Okay, as it expands out one way, it drives these gears. As it cools, it'll start contracting. The ammonia will begin to contract. It will draw this actuator back into its starting position, and it will have a ratchet gear here in the pinion, so it freewheels back, but it forces it one way and freewheels back. It drives these gears. Okay, this is the gearbox here, which drives this shaft here, which is fitted with a large sprocket. This large sprocket is then connected with a belt to a smaller sprocket that drives a generator. All right, your rate of speed for your rack and pinion is about 26 rounds per minute, but these gears will jack it up to about 2,200 RPMs. This generator will put out about 10 kilowatts from this system. So it's a cycle. It heats up, causes pressure on the actuator. The actuator drives the gears, which drives your electrical motor. It has also fitted with a flywheel. This flywheel is to help maintain a steady state at speed and to overcome your static resistance when you first engage your motor. All right. So that's the basic premise of the thermal power generator. You also have a balance tank here, because at the end of each extension and withdrawal, it has to have a period of turnover, and we cannot allow pressure to continue to build in the exchanger. So any pressure above 6,000 psi will be relieved into this tank until it switches mode. Once it switches mode and comes to the lower end of the cooling cycle, it will begin to contract and cause a vacuum within the system, and it'll draw that whatever fluid did get into the tank back into the system. All right. So that's your basic operation of how this works. Now for the practical side of this, you can actually, your average boiler can accommodate 4 units. As we said previously, these units have 10,000, put out 10,000 kilowatt hours. With 4 units, you would have 40 kilowatt hours. And that would be, let's say in a hotel use, a room in a hotel uses on average about 50 cents per kilowatt. Your average average cost is about $2,200 per room per year. These 4 units will provide electricity for 77 units, 77 rooms per year, giving you a savings of $170,000 per year. Well, that concludes my demonstration of this invention, the thermal powered heat exchanger. Thank you for your time.